Hello, my name is Stuart Kozola, and I'm a product manager here at the Mathworks, responsible for our computational finance area. And it's my pleasure today to be introducing you to the topic of responsible AI. And specifically, my talk will be focused on building a responsible AI pipeline. So what I'm really talking about here is how do we operationalize a variety of AI models within the context of them being responsible, fair, ethical, and such. So the structure of my talk is actually going to be broken into three main sections. The first section is going to be introducing you to the area of responsible AI, introducing a framework of how to think about responsible AI, but also give a background on what I mean by the definition of the term AI, or artificial intelligence. The second theme throughout my talk will be how do I take these AI models that are now built in a responsible way and scale them. One of the biggest challenges faced in the industry today is the ability to operationalize the AI models because they're not developed to maintain and operate in the same way that traditional models that have been deployed are. And then the last piece is really about the best practices of building teams that are really responsible for the models themselves. So with that, let me begin by introducing the area of responsible AI and going through that. Responsible AI can also be thought of different ways in the industry today. Many people call it trustworthy or trusted AI, fair AI, bias-free AI. These are a lot of different terms for that. I'm going to go later on in the slide and talk about a framework for how to think about the area of responsible AI. But just recognize that this is a broad area that often has many conflicting terminology, but it's all about building something that we can have trust and faith in is really what we're talking about. Now, before I get into the area of responsible AI, I just want to kind of lay the groundwork of artificial intelligence, machine learning, and deep learning, and kind of give everybody a view of kind of the technology trends that have driven us to where we're at today. So the area of artificial intelligence has actually been around since the 1950s. And then with the birth of the internet and the gathering of more data, and the Internet of Things coming online, we're now getting more and more data from a variety of different sources that actually make machine learning from data, really much more relevant and appealing today. Many of them were not really widely used because of training and using these. They're still computationally intensive. And that's what has happened more recently with the area of deep learning. So not only has the computational ability been there, but now we're architecting many of these models that we've been using in the past to really be more effective, taking advantage of the hardware and the data that's available to them and the new optimization algorithms for hyperparameter tuning. And that's really the birth of the deep learning area, which has been around since about 2010, 2015 is where that really started to take off. And I'll show that in the next slide. Now, why is artificial intelligence so important and such an enabling technology today? It can really be traced back to around about 2014. So there's been an annual image recognition challenge where the challenge was to recognize different objects within images. It's been around for years. The graph on the left here kind of shows you the timeline of that, where they started out with machine learning, and then they moved into the more modern architectures of deep learning, and how they've been able to really drive down the error rates to the level of human accuracy in detecting objects in a variety of different images. Now, it was in 2015 when the algorithms themselves started to reach human accuracy. They really generated a lot of interest from a variety of different people in a variety of different industries. And what was enabling that was these deep neural network architectures, the optimization algorithms that were used to train those, but also the inclusion of hardware, specifically GPUs, for the ability to speed up these kinds of training algorithms. And you can see how that has really changed since 2013 to 2016. There's a lot of investment in that technology, and it just exploded, right? We now have 60 times the training speed that we used to have in 2015 for these models. So this is the enabling technology of why artificial intelligence is important in the industry today. But with that has come a lot of questions, since many of these new artificial intelligence algorithms are black boxes to many people. They're not well understood. Even if you do understand deep neural networks, explaining that to a manager or a chief risk officer can sometimes be a challenge. So with that has been some more guidance on how do we actually make sure that the models that are being developed are good as the other ones we've used, where we had full transparency. So the first guidance that came out was by the Monetary Authority of Singapore. And they were really focused on what's called the FEAT principles, or really fairness, ethics, accountability, and transparency. So these principles started to become what is known as responsible or trustworthy AI. And that was kind of the initial focus on let's build these models under these principles. More recently, within the past year, you've seen the Federal Reserve Board of Governors actually release a request for information on how financial services industry is currently using AI. The regulators are very interested in understanding how AI is deployed, how they can actually bring that into their guidance that they're doing, and make sure that they're developing policies and guidance that is most relevant and useful for the area of artificial intelligence deployment in the financial services industry. Now, another one that's related is one that was published recently by the U.S. Government Accounting Office, the GAO, which I like this one because it kind of breaks out a different viewpoint that I haven't necessarily seen in finance today. But you can look at, they talk about the data, the governance, the monitoring of the models and performance. But within each of those sections, they talk about the AI model development itself, which is what a lot of the focus in finance has been. But it's also about the operation. So what's the data being used? How's the model performing in operation? What's the governance for an operational model versus the governance around developing a model? So they kind of separated out the difference between when I develop a model and operationalize it. So with that, I'm going to introduce this as a framework for thinking about responsible AI, particularly when you're looking to validate AI models. What are some of the questions you should be looking at? They fall into really these 6 areas: safety, explainability, interpretability, fairness, security, and robustness. But before I get into that, here's some different approaches that can be used in the different areas. So like for explainability, some things you can do is global explanation, local explanation. A lot of Lime and Shapley are kind of derived in that area. Other things for interpretable could be, similar. You have global and local for the interpretable model, but really the interpretability means more about the structure and the mechanics of how the model is making the decision, not necessarily the features and the why. I'll explain that in the next slide. And then a variety of other things. But in the interest of time within this presentation, I'm really going to highlight these 3 by example. So I'll show you a visual explanation for explainability, adversarial attack for robustness, and then adversarial debiasing for fairness. So before I get into that, let me just kind of explain the difference between explainability and interpretability. So over on the left is kind of a good example of what explainability is. Explainability can really be defined as it's the why is an algorithm making a decision in human readable or interpretable form, right? So the image here on the left is a schnauzer. It's a dog that has bushy mustache and eyebrows. It's very characteristic of a schnauzer. The hotspots you see on the image are kind of weightings of the feature importance that help make a decision that this image is being classified as a schnauzer. So you can see here that you can understand why schnauzer was the actual classification, but you don't know what was the algorithm that actually did that. How did it actually identify that this was a schnauzer? That's the difference between interpretability. Interpretability is actually going through and understanding what within the algorithm logic or process led you to that conclusion or to that classification, right? The example on the right is an example of a decision tree. It's really, looking at how many bicycles will be rented given a certain temperature within certain days. And you can see the logic chain on the left that went through to make a certain decision. So decision trees are very transparent, easy to interpret. Machine learning models, like deep learning models, are not necessarily as easy to interpret. And to give an example of explainability in the credit process area over on the left, there's an example. Many people develop models with the predictive outcome in mind, but not necessarily developing the model with the intent of making it explainable to the business users or the consumers of the algorithm. Right? So rather than developing an algorithm that just says you're approved or not approved for credit, it should be actually explaining why. So here's an example where you're not approved for a credit because your age is under 25, you have a low salary, and you have unpaid bills greater than 3 recently. So that actually gives you the explanation of why the model says you're not approved for credit. And that can be done by building in explainable characteristics within the model construction stage itself. But giving an example of how you can do explanation through visual, this is an example of how you can do the explanation and interpretability of a deep neural network model. So over on the left is actually a deep neural network model that does image classification. This was built on something we built at the Mathworks, where we had the Mathworks community contribute pictures of food that they ate with over a 6-month time period. And then we trained an algorithm to actually classify the different images. In this case, it's showing you that there's a Caesar salad, French fries, hamburger, pizza, and sushi. The plot down below, the kind of the network architecture diagram above it, is actually the input data set. So it's the semantic clustering of the data on input to what was the output. So this would be the output layer. And you can see how the input categorized by the different types of food they were, and then the output actually was able to separate them and put them into clusters and classify them with some probability that they belong to one of these clusters. Now the image that's been animated over on the right is actually visualizing that semantic clustering as you go through the different layers within the neural network architecture. And then it gives you a feel for how the neural network is pulling apart and teasing apart the differences and looking at different features, and then eventually getting them into the separation of the clusters. Now this is just a 2D representation. There are many more factors, so you can look at many other factors on the different dimensions to even dive in more detail and really understand more about the feature characteristics that we're doing that. But this is a good way to explain how an algorithm is functioning, because many people are visual and can really understand this very quickly, rather than understanding the mathematics behind how the separation was happening. Now, when we talk about fairness, bias really comes up as the main source of fairness in many cases. And there's bias, a definition from a statistical sense, which is really just the unequal treatment of different groups. And then there's fairness, which is really about bias. There's fairness, which is really about detecting and mitigating any differences in the bias or the unequal treatment of underrepresented or underprivileged groups. And really, there's kind of three different sources or approaches to that. One is that your data sets you need to look at. In many cases, the data are biased because of their construction. They're lacking different genders, different racial ethnicities, or other things you might be of interest. So there's just not enough data to really train a model that can understand bias. So that's where you get bias through the selection of the data. The other thing is you might be using organizational data that was trained and used based upon the operation of an organization, which has its own inherent bias in the way that it's operated over the years. And that inherent bias will be reflected in the trained model because it's learning from the data sets you have. And that's really called legacy bias in the data, or really the bias from behavior of how that data was actually collected and used from the source. And then the last part is actually the model itself. Is the model built in a way where it introduces a bias that it shouldn't have? So that would be the modeling issues themselves. It's either not capturing a characteristics or it's overweighting a characteristic, as an example. Or one method to actually go about, debiasing a model, and this is actually doing that in the actual model itself versus doing data pre-processing or model output post-processing, is to look at adversarial debiasing. So when you build an architecture of a model, in this case, this one is using input embeddings, a shared hidden layer, and then a prediction label. That would be the normal way of building a predictive model. But what you do is you also add another output variable that you're looking to predict and optimize. So you want to optimize the prediction label Y, but you want to minimize the impact that the sensitive attribute Z has. And you do that by introducing that other predictive capability as the model output, and then running a optimization or hyperparameter tuning optimization on the entire model. And that'll build a model that actually reduces the sensitivity to those attributes that you most want to remove from your biased outputs. And the great thing about this is it can really be applied to any bias metric. It's not tied to a specific one. It's part of the modeling process, and you treat it as an objective of the outcome of the modeling process. So in the area of robustness, one thing to keep in mind is that, when you're training on lots of data in the data set, there could be a lot of sensitivity to that finite vocabulary, particularly when you're looking at classification types of problems. So when you're looking at classification, you usually have a labeled data set that's probably built with a certain amount of finite vocabulary. And if the algorithm sees something that's outside of that vocabulary or outside of those categories, it doesn't necessarily know what to do with it. And this is a good example of how you can uncover that from your model. This is just doing some simple things like omitting data, changing pixels, doing image rotation. This particular example is showing you a stop sign in one image over on the left, and it's correctly categorized as a street sign. And over on the right, because it was rotated, it's not really identifying it as a street sign. It thinks it's a laptop based upon the angles of some of the features that are there, I assume. And this is an example of how just simple rotation of the data or simple playing with the data input can reveal how robust and sensitive your model might be. There are other ways to do this as well. And I showed you that on a couple slides ago. But this just gives you an example of how you can test it for robustness. Another way for doing that, but also looking at how you can build simulated data, is using generative adversarial networks. And what this is really taking two models, having one model that's trying to discriminate real versus false, and having another model that's actually trying to fake out the other model. So it's you can think of it as an adversary that's really trying to test it. You can use this to test your models. You can also use it to generate synthetic data. So this example is really showing how you can use random noise as input to the generator that can generate fake images, in this case of facials, of faces. And the generator keeps going through and gets tuned until it's to the point where it can create faces that can actually fool the discriminator. And this is the way of using generative adversarial networks in a very effective way to challenge your existing models, or even using them to build stress testing scenarios or synthetic market data, because now you can do that from the generator network. So that's kind of gives you an overview of responsible AI and a couple examples in some of those areas that we talked about. Now, what I want to get into in this next part of my presentation is really how do you scale these models and get them into production. And one of the biggest barriers we're seeing in the industry today, that's recognized pretty much by everybody, is that it's difficult to deploy these new AI algorithms into the existing production infrastructure that we have. And that's the number one challenge of being able to actually operationalize the value that we have in these new artificial intelligence algorithms. And part of that really because, the legacy of the system, the architectures that we're using are different companies. are different. They built up over time. There's inconsistent run times. There's a variety of different tools that are used. There could be poor quality models that are built from this. It results in regulator scrutiny, high cost, inconsistency, frustrated users because of the environment wasn't really built to scale to the point where we need it today. And that's also becoming more and more complicated because we're not introducing simpler models. We're actually introducing more complex models, and more complex models that have more complicated data input requirements, larger data input requirements. And then, of course, there's disruptive things in the environment or regulatory or even social environments that are causing more disruptive change on top of this. COVID-19, the need to move to virtual environments, the push for sustainable climate change, ESG, those kinds of factors are all helping disrupt things. So really, when we think about it, how do we go from the development of these new algorithms and the research teams to actually operationalize them in productive environments? And how do we get through this through the implementation, deployment, and integration challenges? Because now you're introducing AI models that often have more feeding and nurturing than other models might have needed in the past. So the idea is to go from this state to a continuous model delivery system or ecosystem. You can think of this as the whole model lifecycle just seamlessly working together. And the way that can be achieved is to actually focus on how the work is done across the lifecycle, the different people that are involved, and what they truly need to get their work done. So you have the model developers who need the ability to really define models. It's not just the programmers, but it's also the business analysts and the mathematicians or quants that would like to get their ideas into the model development stage as early as possible, most likely in an environment or language that supports them best. So you want a model development environment that speaks their language of thinking rather than speaks a language of implementation. The other thing is that somebody's going to have to review and sign off on these models. So how easy is it for them to dive into the model, see the history of development, some of the assumptions, maybe even play around with some of the parameters so that they can get a feel for how sensitive these models are to that. And just understand that this model is ready to be approved for the next stage and implemented in a business environment. And then, of course, once you've got an approved model for use, now you then have to do the exhaustive testing and validation upon those models to make sure that it's operationally ready. You found all the security vulnerabilities, you found any robustness issues, you found any privacy or security issues from data leakage is another example. And then once you've gone through the model testing and validation, then it goes to the actual execution environment. Where does it live? Can it scale on-prem or in the cloud? Do you need other integrating technologies for that? Modern neural net or modern artificial intelligence ecosystems actually can contain many artificial intelligence feeding into the same pipeline. An example would be where I'm using a feature engineering approach that uses an artificial intelligence algorithm to generate features for a downstream model that might be used. So now you have multiple artificial intelligence models linked together. So that dependency really needs to be captured, and how does that get deployed into an execution environment that can recognize the vulnerabilities and linkages between them that could cause failures. The other part is, building the ability to discover and look into the models and how they're performing throughout the life cycle, not just from how they're performing in production, how are they performing in development, what stages are they in, what were their approved uses, how many models in different states do we have, for example, for the chief risk officer, so he can have visibility into the entire model development cycle of his organization. And then, of course, kind of the cornerstone that brings all of this together is the model inventory and model repository or data repository that kind of glues all these pieces together, provides that insight, provides the information gathering and reporting mechanisms that are needed to provide fast feedback or insight. And of course, the environment or platform you want to scale across, big data, be AI machine learning ready, can adopt agile practices, be secure, cloud ready, and has a good ROI. So the real question is how do we get from the ideal state, or how do we get to the ideal state from our current state? And really, when you look at kind of the requirements behind there and the challenges and pains that people see, they fall into these general 4 categories. And really, when you go from the current state to the desired state, there's a pain to overcome within each of those that have been categorized really in these 4 big pains to overcome. It's the challenge of being unable to integrate and automate all the tools you're using across your modeling lifecycle. The high cost because of data redundancy systems, platform systems, a variety of other complexities there, and the need to rework many things in many cases because you might be taking the model from Excel and recoding it into a production deployment environment. So there's high cost with that. Then there's a limited visibility and traceability because you have these different silos and different sets of tools. How do you know where the state of the model is across all of these? And that really impacts the quality of what you know of the model to be throughout the life of it. And then, of course, the real important thing for being able to innovate and drive disruptive change within the organization is the lack of timely access to the decision-making or risk metrics of your models. So all of these really kind of fall into those 4 main categories. And then there's real kind of four broad capabilities to think about when you want to try and solve those challenges and move from the current state to your future desired state. And really those fall into the categories of, is your platform open and interoperable? Does it enable uses by novice experts and users? Is it scalable? Can you scale it both horizontally, vertically, integrated documentation reporting? Have you maximized automation, particularly in today's remote-driven world? You really want to have automate as much as you can. And then also, do you have the ability for fast feedback? Now, the items highlighted here in orange are the things I'm going to talk about on the next slide in some detail, but recognize that there are many different things, and different things might have more importance to different organizations. So one of them is enabling use by the novice users and experts. Does your platform allow you to take and develop citizen data scientists or citizen quants, or even, can a business analyst do something that someone else in the organization that's highly trained be able to do? And that's, do you have a library of pre-trained models that can allow them to do incremental learning? So learn how to use a model that's been selected for appropriate use, tune it for something new, and now you have a new model for the organization. A lot of this is derived from the deep learning and incremental or transfer learning that's happening, but can you import models from a variety of different environments, such as TensorFlow, Caffe, MATLAB, reuse them in a different platform? And how easy is it to dive into the architectures of these complicated models, inspect them, tune them, and make them usable for your environment? Now, this is an example of a no-coding environment for building and constructing a deep neural network, as an example, and how you can do that without any code. But also as important as this is how you get code from these, or models that can be implemented in code from no-code environments. And this is an example of, once you've built a neural network, you've got the neural network trained, it's defined. Now you can generate a pre-trained model that can be generated in terms of not only the code itself, but a document form that somebody can read through and understand what this model is doing from a coding perspective. So it enables the handoff from the business analyst who built a new model to somebody who might have to implement it in another environment. They have a recipe right here to do that. So it's the ability to reuse and automate what you're using. The other thing under the scalability is how automated and integrated is documentation into the process of the model development itself that you have. This example shows how to use live notebooks that really kind of provide drop downs and sliders that can actually allow someone to dive in, look at the assumptions, play around with different parameters of the model, maybe even change some of the data and see how the model responds. So it allows the interactive documentation and exploration. So you spend time evaluating the model, not documenting the model. And that really provides the ability to get things out the door faster, because now you have an understanding of how the model is truly behaving. And the documentation itself becomes part of the model. So you have the model is the documentation, is another way to think about it. And then, of course, you do have to adhere to a variety of different reporting templates and formats. And this is an example for creating a model validation report for, say, a regulator or an internal model validation team. One thing that you can do here is you can actually tie your templates or processes you have in the organization back to the source code. In this example, we're showing you how to add holes to a Microsoft Office template. The holes themselves will allow you to put in tables or figures or a variety of different mathematical equations that might come from the code itself. And this example will link back to the code, which is live. As the model changes, you can quickly regenerate the documentation. And just to kind of show that, here's the example of linking it back to a model built in MATLAB. You can go through, look at the model itself, the variables in the workspace, what was the data that was used to drive the model. Maybe there's a model update that needs to be done because it came back from a reviewer that said, should you consider this? You can then click the button over here that says refresh, and it'll refresh the documentation with all of the figures, the tables, and the data from that new model. So it makes it very easy to do incremental model development and documentation. So you remove the burden of documentation and spend more time innovating on the model itself. And the model becomes kind of the live referenced artifact. The model itself can generate the documentation at any state. So now you don't have a disconnection between the model and the state of the documentation. Another way of looking at fast feedback is, are you unlocking the ability for experimentation of ideas within the organization, right? So if you've done a lot of automation, now you can move to the fast feedback, diving into things or playing around with a variety of different assumptions. The example image over here on the left is something we call the experiment manager, and this allows you to manage a variety of different models and the different experiments that are used to tune them, different data sets, different hyperparameter tunings, or different models themselves. It keeps a log of all the different things you do under the development process of building a model that then gets approved for production use. And over on the right is something we're calling a templated model use, and this allows you to build kind of a recipe for building models with a drag and drop or scriptlet kind of framework is what we call it. So over on the left, you can see a variety of different categories of things that you can drop into. They're little, you can think of them as tasks or sections of code that come with documentation already pre-written. You go in, you customize it for the model you're building. It allows you to very quickly build up and document a model through a checklist or a process you might have within your organization. So this is completely customizable to the way the organization would actually build that. So the last section is really talking about building the practices of cross-functional agile teams. And really we talked about the technology for deploying models into operations. It's well recognized that model operations is kind of the bottleneck for being able to really get value out of these models that we're building. But we also have to think about how these teams align and work in their workflows. So if you think of a modern organization as a model risk management framework, there's the first line of defense that are building the models. And it includes the development team as well as the operations team. Then the second line of defense is the independent model review. And how those people integrate and operate can actually have an impact on whether you have a waterfall process or an agile development process. And this is just an example of, the image on the bottom is kind of a representative of a modern model DevOps process, and then validation is kind of should be overlaid on top of that and have visibility into both. And how you integrate those teams is kind of the key to your success. So over on the left is really the plan for model development. Over on the right was what I showed you kind of as the life cycle wheel. But the main thing to think about is how you're constructing teams that take advantage of the technology and tools you're providing them. And that really you should consider using agile frameworks, because they're actually been proven to kind of develop teams that are self-organizing that can actually deliver and own the process themselves. So this is really about empowering the teams to deliver the vision that you have for the environment. And if you don't know about Agile is really an Agile manifesto. It's really around software development, but it can be applied to many different things. Here at the Mathworks, we tend to use some Agile techniques within marketing itself. But really, it's favoring individuals and interactions over the process and tools that you have. It's always building working artifacts or software, making sure the customer is always involved within the development process. The earlier their feedback can be getting, the better you can be at satisfying requirements and avoiding rework. And then, of course, just recognize that change is going to happen. Build it into the way that your teams function and are structured. And that can be really kind of thought of in terms of best practices in these different kind of categories. You've heard of the small pizza teams from Amazon, or the 2 pizza teams, about 6 to 10 people. That's really about favoring individuals in interaction. So building a team that owns the whole process. That's kind of critical to making sure this happens. And it needs to be a cross-functional team so that you can get the viewpoint of not only the developers, but the teams from the operations, or maybe even teams from the validation. Favor working little prototypes, even if they're on paper, to actually building something out and then delivering it. So do iterative refinement and delivery. Customer collaboration face-to-face, deliver concepts early and often to them. And then, of course, responding to change means build change is kind of a competency within the organization. But then also think about automating everything. Practice continuous model validation, model documentation, model integration, and model delivery. Now, when you actually do that, here's an example from a customer we had that presented at a MATLAB conference, I think 1 or 2 years ago, that talked about their experience with the modern waterfall lifecycle that they were using on the top. Took over 2 years to actually develop and deliver a new model. And then the agile model lifecycle once adopted down below, which took less than a quarter or 3 to 4 months to actually implement. And the keys to this is that you're actually involving all the stakeholders throughout the entire process, and not just at the end when something needs to be delivered. And that's one of the biggest challenges I've heard from many model validation teams or model development teams, is that they often went to the model validation person who vetoed their project because they didn't have a good sample data set. Their data wasn't information dense enough or wasn't appropriate for their use. So 6 months of work was thrown out the door because of that, when that should have actually been recognized almost from the first month of work. So this is just an example that, these principles I've shown you are not just, philosophical, but when put into implementation, you can actually have a real impact on how you can deliver models into the organization. And it's even more important nowadays when you're looking to develop more complicated and more complex models in terms of the artificial intelligence ones that are out there today. So with that, that's my talk. Thank you for attending.